M.Röckner is a professor of mathematics at Bielefeld University. He has had previous professional positions at Purdue University and the University of Bonn and was a reader at the University of Edinburgh. He received his doctoral degree and his habilitation from Bielefeld University. He has won Sir Edmund Whittaker Memorial Prize, the Heinz Meyer Leibniz Prize, the Max Planck Research Prize. In 2017, he was awarded an honorary Doctor of Science degree by the University of Swansea. He is a distinguished visiting professor at the Academy of Mathematics and System Science in Beijing and won the award for international cooperation for the Chinese Academy of Sciences in 2003. On 24 June 2024, he received the International Science and Technology Corporation Award of the People's Republic of China. He is a member of Academia Europaea, the Academy of Science and Literature, Mainz, and a foreign honorary member of the Romanian Academy of Sciences. He is the president of the German Mathematical Society and the director of the Center for Interdisciplinary Research in Bielefeld. He served as a panel chair for advanced grants of the European Research Council, as the member of the selection committee for the Senior Humboldt Awards, as the member of the Senate's Commission for Collaborative Research Centers of the German Science Foundation (DFG), and for 11 years as the deacon of the Bielefeld University's Faculty of Mathematics. Apart from 6 books, he has published close to 400 research articles, supervised 31 PhD students, and was the host for 10 Humboldt Scholars. His main field of research is stochastic analysis. We are very happy to have you here. You may please begin your talk.
No, thank you very much for the kind introduction, but I was the dean. I'm not the present dean. I just want to say that. Otherwise, the present dean will be not so happy. Okay, again, thank you very much, and also for the opportunity to talk about this part of my work. So it's about nonlinear Fokker-Planck equations. So this is one major area I'm working in, and on the other side, stochastic differential equation of McKean-Vlasov type. And today I will do a case which is interesting for this seminar series, namely the case when the Laplace operator is replaced by a fractional Laplace operator. And then in the SDE, of course, the Levy noise will appear. And I would like to explain this today a little bit. So this is joint work with Viorel Babel from the Romanian Academy of Iași, Romanian Academy at Iași. And so it's supported by our grant from the German Science Foundation. And Viorel and I, we have several papers on the subject of nonlinear Fokker-Planck equation and McKean-Vlasov equations. And the most important ones I've listed here, and they will also be cited in the text. So the main paper I'm going to talk about, the paper I'm going to talk about today is this one that just came out in PTRF. And I also would like to point out this recent Springer lecture notes of Viorel and myself. And I would also like you to check the references therein, because today in the talk I will not give too many references to what other people have done. And there is, of course, a lot of contributions to McKean, in particular to McKean-Vlasov stochastic differential equations, which are from a different perspective, namely using probabilistic techniques like propagation of chaos, for instance. But this analytic approach to start with a nonlinear Fokker-Planck equation, there's not so much in the literature. And but nevertheless, I would like to ask you to check this book for references. Okay, so now let me start with the contents of the talk. And first of all, I would like to show you my favorite slide, which gives a motivation of what we are doing, and also about our long-term program. So some of you might have already seen that those 2 pages, but I think they are important in order to locate what we are really doing within the general area of stochastic analysis. Okay, and then I will talk about the fractional porous media equation perturbed by a transport term, and there is the Laplacian usually in the classical porous media equation, and I will briefly recall that. But today, as I said, I will concentrate on the case when the Laplace operator is replaced by fractional Laplacian. And then I will also show and maybe this is another talk, about the case when the power in the fractional Laplacian is replaced by a Bernstein function. Okay, and then there will be a section on the existence of distributional, so-called distributional solutions to the nonlinear Fokker-Planck equation with the fractional Laplacian, then about uniqueness of these distributional solutions, and then comes the applications to McKean-Vlasov equation, existence, uniqueness, and rising nonlinear Markov process in that situation, so in the sense of McKean. So this is first of my favorite slides. So this is about our motivation, long-term goal. So I start here with the most classical case you could think of, namely there is always, what I'm telling you about is an analytic part. So that's given by the Fokker-Planck equation, and then the nonlinear Fokker-Planck equation and the probabilistic part. And of course, the most known example is that of the heat equation on the analytic side, and then on the probabilistic side, it's Brownian motion. So let me briefly recall this relation. So of course, there's relations in various ways, but I would like to pin down that the relation that we are going to generalize to nonlinear Fokker-Planck equation. So here the Fokker-Planck equation is simply the classical heat equation. And this variable y is the variable with respect to which I differentiate. And the x is a fixed initial condition given by the Dirac measure. So if you want to solve this equation, it can be considered as a so-called Kolmogorov forward equation because we have a differentiation in the forward variable and the backward variable, so the initial condition is fixed. The backward equation you differentiate with respect to the initial, so the initial condition. Of course, for the Laplacian, it's the same because the solution is symmetric in x and y. Yeah, but I stress this because in a moment it will, okay, in the next example, it will still be symmetric in x and y, but then in general not. So in a sense, the Fokker-Planck equation is a forward Kolmogorov equation. Anyway, the solution now where consider x as the initial, this refers to the initial condition, everybody knows is just a classical heat kernel. So that's the shifted normal distribution, standard normal distribution, if you think of this in terms of probability. So it's a probability density. The corresponding process is the Wiener measure. Sorry, is the Brownian motion. So the corresponding measure is the Wiener measure. And we look at Brownian motion started at x. So we look at the space of all paths that start at time 0 at x. And we look at the corresponding Wiener measure. So it's just the shifted Wiener measure with respect to start at 0. And then, so everything now, since I'm going to talk about also weak solution of stochastic equations in a moment, so everything, all the information is in the measure. Yeah. Okay, so that's the measure on this path space. So then we can look at the canonical process, the canonical Brownian motion now. So as Wiener, Norbert Wiener constructed this measure, I should mention this already in 1920. And the corresponding process is now simply the evaluation process. So we look at the paths in my space of, well, events. This is my space of events, omega. We look at such an event, and then we just evaluate this path at t. Yeah? So then we get the stochastic process. Yeah? So t is running, so this gives me for every w. So w is now a path, gives me a point in Rd. Okay, then I can look at this Wiener measure and I can look at the image measure under the path at time t. So this is what is called the time marginal law, yeah, the one-dimensional time marginal law, to be more precise. So then this time marginal law is given by the heat equation. Everybody in the audience will know that. You know? So that means by the solution of the heat equation. Now this is a measure on Rd, so for fixed t, and the initial condition is Dirac measure at x, yeah? And then the time marginal law is of this, so is simply this image, yeah, under this map, is given by the heat equation. And then if you do this for any initial condition x, then you get the corresponding Markov process, which is a family of measures, namely all these measures for all initial condition. And then you simply look at the canonical process because I look at this canonical probability space. So now so that's the probabilistic part, and now this relation becomes one-to-one. You might protest because everybody in probability, of course, knows that the path-based measure is not uniquely determined by its time marginal law. However, if you look at this bunch, at all the solutions of the heat equation for all initial conditions, delta x, so for all initial points, then they're really in one-to-one correspondence. So that means you can reconstruct, if you know the solution, then you can reconstruct the full Wiener process. Yeah. Okay, you might have in mind in order to check whether what I'm saying is correct. This gives you the transition semigroup, and then just do the usual convolution of the semigroups, and you get the finite, so the finite dimensional time marginal laws. And then, of course, the corresponding path-based measure is uniquely determined. You can think of it this way. Yeah. Okay, but one can also think of it in the terms of Stuck-Varadhan's martingale problems, because we know that if we have two martingale solutions, and they and for every x, so that means we have a family of solutions, and at every x their time marginal laws, so start at x, for every x the time marginal laws coincide, then the two martingale solutions coincide. That is basically the same in probabilistic, in path measure terms, and also analytic terms, rather than look at semigroups here, and convolution of semigroups, or composition of semigroups. This may be better. Anyway, so there's a one-to-one correspondence between these two objects, analytic and probabilistic. And then, of course, there's a big theory has been developed, I mean, basically since the 50s of last century, namely the theory of linear Markov processes in relation to the linear parabolic PDEs of a certain type. And these are exactly the linear Fokker-Planck equation. So it's a big theory, a very successful theory. So there are very famous books about this, like Dinkin's book, or Etienne Kurtz, or the book by Struck, the book by Struck and Varadhan, and so on. And you know that this was a very successful story, because there are many problems about parabolic PDE, or the corresponding operator, here is the Laplacian, can be reformulated as a problem of the in the Laplace case, a Brownian motion, or a problem of the corresponding Markov processes. So think about hitting probabilities, capacity, and sets which are not hit by the process, and so on. There's a really huge amount of results, and there are still being results newly proved nowadays. So it's really a success story. So, because in general in mathematics, if you have two different ways of looking at the equivalent mathematical objects, like it is true in this case, then this is really a start usually of very intensive research to go from one to the other and vice versa. Okay, so now our dream is basically, well, this dream is due to McKean to do the same thing for nonlinear Fokker-Planck equation. Now let's look at this nonlinear case, and this was one of the main results of in our research project in the first period, this connection, to exploit this connection and also discover this connection. Okay, so now we look at the nonlinear case, and the classical equation we are going to look at here is less canonical, of course, than the heat equation. It's the parabolic Porous-Media equation. Yeah, so that the only difference between the previous page is that here this m is not necessarily equal to 1. If it's equal to 1, then we are back to the heat equation. So we look at this at m for m bigger than 1. You can also look at it for m less than 1, but this I will not talk about today. Okay, just to keep it simple, mainly on the analytic side. Okay, and then you do exactly the same. You look at the solution for with Dirac measured initial condition. So this x is now the initial condition, and I look forward. So I take my derivatives in the forward variable. Okay, then the corresponding fundamental solution. So the solution with Dirac measured initial condition is well known. It's the famous Barrenblatt solution. We are working on all of RD here. And there is a formula like this. So that means, you see, it is no longer exponential, e to the minus exponential, the difference of these two guys, squared, but is now is kind of a monomial. Yeah, so there is this power here that depends on this m, and the beta and alpha, here's an alpha, this depends on the dimension and m. So here are the exact relations between the two, and then this k also depends on m constant d only, yeah? But it is written more, let's say, easily like this by using this constant. And then the c is chosen in such a way that make this a probability measure. No? So then you can imagine if you change it c, then you see here's a plus, then where this is not zero changes drastically. And so you can think of the volume below this curve over RD, and then you see, of course, that you can make it also a probability measure. Yeah? This is an intuitive way of understanding this. Okay, so then we can also ask, do we have on the other side a corresponding probability theory? And the answer is the following, that there exists a probability measure Px on the space, again, the space of paths started at x, such that enter stochastic process xt, and this is no longer just the evaluation process, because we want to compare this process with the Wiener process in a moment through an SDE. So this is some process, and if I look at the time marginal law of this process, so the image measure under xt of the measure Px on path, then this is given by the Barenblatt solution now. So more precisely, the corresponding probability measure with the Barenblatt solution as a density. And this measure is can be thought of simply as the law of the solution to this stochastic differential equation, which I will explain in a moment. But it can be looked at the law, so that the image measure of the Wiener measure under this x. Yeah, so that is exactly this Px. So the path law of this is a path valued map, right? So that means this path is mapped onto a new path. So this is path valued. So then I take the image measure. So I get again, if I take the Wiener measure here, I get again a measure on this space. Okay, and that's my Px. Okay, and then what is the x? The x turns out to be the solution of the following differential equation, stochastic differential equation. So dxt is again dwt, so as before. Initial condition is delta x, as before. But then we have this diffusion coefficient in front. So in particular, xt is a martingale. Yeah? So that we have this diffusion coefficient in front. And this diffusion coefficient is very special because it depends on the time marginal law of my solution. Yeah, so that means I have to so I take this Barenblatt solution, which is the law, we should not forget, of our process, the time marginal law at time t, and I evaluate this as a function of x and t at x, so this refers to the initial condition, and then we have x of t here, so the process itself. Okay, so that's a very particular way of how the xt depends on how the right-hand side depends on the solution. It depends on the solution in two ways. The first way is take its time marginal. So you can maybe call this for a moment L sub xt. So this depends on xt, on the solution. And then you evaluate this time marginal law, which is a function, the density, at the solution xt. And here you can see is reflected the nonlinearity. Yeah? So this m-1 now is here. Okay, so if the m is 1, so this is the heat equation, yeah, this is no longer there, then this is not there. This is just 1. And then we get again Brownian motion. Okay, and then what is our main contribution is then to prove that this really forms the Markov process as well, a nonlinear Markov process. And again, then we have the full correspondence between this family of PDE indexed by the initial condition and this Markov process indexed by the initial condition. So these Px are very related in a very intricate way. It's not like in the Brownian motion case, we just shift the initial condition. It's quite complicated dependence. So, if we compare two measures, there is a relation through the Markov property. And this is a very complicated relation because it reflects completely the nonlinear PDE, which is also not an easy object. So in a sense, the nonlinearity here goes into and I stress, we have to look at all solutions at once for all x. Then we have a one-to-one correspondence between the two objects. Yeah? So it is not that if I fix, we cannot do it xy. If I know x here, yeah, then I can determine px. No. I have to know all solutions, yeah, exactly as in the Brownian motion case, in order to determine these path-based measures. Okay, so that is then what could be called a nonlinear Brownian motion, but is not the nonlinear Brownian motion because there is an m here as a parameter. So therefore we put this in quotation marks. But in some sense, it's an analog, a nonlinear analog of Brownian motion. And these are the papers that they mentioned. This is the paper in the papers on of probability. And then there is a general paper about nonlinear Markov processes. And then the paper where we first realized that we have the Markov property essentially is already here. And this is McKean's dream because he suggested this. So take a nonlinear PDE, this type, and then try to prove that the solution is the time marginal law of a Markov process, like Brownian motion is for the heat equation. Yeah? So he wanted a Markov process with this property. He didn't do it for the Porous-Media equation. He just he talked about Porous-Media equation at d = 1 as a possible example, but he did not prove it. But this paper is not so long, in PNAS 66, 6 pages, and so he had some, let's say, visions or ideas what kind of equations he has in mind. In particular, he gave more details on the Burger's equation. That's another example for this. Okay, and now our dream is to extend this kind of relationship through, in particular, the corresponding SDE. So we have a very nice understanding, in a sense, of what is the corresponding Markov process, because it's a path law of an SDE that you can write down explicitly. And so we would be, so our dream is now to extend this to more general nonlinear parabolic PDE, again of Fokker-Planck type, so you differentiate in the forward variable, and on the other side of the probabilistic objects, nonlinear Markov processes. And this is what McKean defined for the first time in this paper, but what is a nonlinear Markov process? I will, if I have time, I will recall the definition maybe in a little bit, maybe technically more explicit form. Yeah, so this, but in principle, it is the definition of McKean. Okay, so then we took up basically the challenge, or the maybe it was an order, I don't know, of McKean, and we try now to realize this program in very, very general situations, and then try to understand the nonlinear PD through the corresponding nonlinear Markov process and the other way around. So for instance, one question could be, can you prove for such type of an equation whether there is an invariant probability measure? Yeah, of course, it's not true for such an equation, but maybe if you add a certain drift, like you do to the Brownian motion, if you add a linear drift, you look at the Ornstein-Uhlenbeck process, then suddenly it has an invariant distribution in a stationary law. So the normal under this starting distribution becomes stationary. Or other way, there is a if you add such a term, so for instance, in the case of Brownian motion minus identity, then we know that there is a corresponding stationary solution. So there is a solution where the left-hand side is 0, so it doesn't depend on time. Yeah. And so we did this already, also for nonlinear Fokker-Planck equation, but we need to add a drift in order to do it also in the nonlinear case. So we use the nonlinear PDEs in that situation in order to find a stationary solution to the nonlinear Fokker-Planck in order to find a stationary solution for the corresponding process. Okay, so now let's look at such equation which are perturbed by a first order part, and it should be a forward equation, so the dual equation, or backward if you like. So the drift should be of a transport type, so there's a divergence of a drift, and let me explain a little bit, so not what I mean by that. So you see, I have replaced here, first of all, I have used rho instead of u for the solution, because we think of rho later on to be a time marginal density. So then densities in probability theory usually denoted by rho. And then instead of taking just the power here, as in the classical porous-media equation, we take a general diffusivity function, as is usually done when you study a porous-media equation in analysis. And then we add this drift, and this drift is of a simple type, relatively simple type, as you can see, in the sense that there is a linear path. So this is just a vector field on RD, and this is a real valued function that depends on the law. So it is kind of a tensor type nonlinear function. Yeah. So this depends on the law, and this depends on x. Yeah. Okay, and this helps in the analysis quite a bit. It's not really necessary, but then results are more explicit, and in particular, we have quite good uniqueness results that I will explain in a second. Okay, and then in general, you cannot start these equations at every Dirac measure, or at every measure in let's say, any measure of bounded variation. Doesn't even have to be a probability measure. So that you take all signed Arran measure. And then under certain condition on beta, D and P, you can solve it, but it's not always possible. Sometimes you have to take a smaller space. Okay. And now we use this equation. So we developed a solution theory, of course, with the help of many analysts who did a nonlinear semigroup theory, but they have not studied this equation, but related equations. So that's, the machinery was there, but of course, it's always the difficulty to apply a machinery, and that is basically what we did here. Okay, and then our idea is to find the corresponding solution of the SDE. So this is our business, so to speak, because suppose we know the solution of this equation. And this equation now, you have to be careful. You see, here's the solution of a nonlinear Fokker-Planck equation. But we also want, remember the Prost media case, that the XT has a time marginal law given by the rho t. Yeah. So exactly as in the Prost media equation. So in a sense, you have two equations, like here. Yeah? You have this equation, and you have this equation to fulfill. And we do the same here. Yeah? And now, once you understand this Fokker-Planck equation structurally a little bit better, you can immediately write down what the corresponding SDE should be. And in this case, it's this one. So the beta divided by rho is exactly this part. I mean, if you take this beta, yeah, so this is a simple generalization. And then there is this 1/2 is also here. Okay, so when you have a bit of experience, it's very simple to write the corresponding SDE. And the point is then to see how it is related to this one. And the thing what you do is the following. You take the XT, and then you write down the corresponding equation for the law of this equation, for the time marginal law. That means for this rho t. Then you just, this you can just do by Ito's formula. And rho Dinkin formula is simply Ito formula in an integrated form. You take expectation, and then you get this equation immediately. Very, very simple. So once you know this, then you know, okay, this is this will be the corresponding equation. But to go from here to here is much more difficult. And the difficulty is that we have to fix for the corresponding law of this process, not only the initial condition, but we have to fix the marginals. Okay, so you take such a marginal here, rho t, and then you have to find a measure so that solves this equation for the rho that we found after solving this equation, and we solve it first. And we have also to manage that this law, it's always a measure on path, has time margin laws given by the solution that we found up here. And what is behind here is the so-called nonlinear superposition principle. It is a nonlinear version of the usual of a known superposition principle, which exactly does this. So I don't want to spend too much time on this, but so this is the way how we go from top to bottom. So now let me go finally to the fractional case. So so I will not give you precise results in this case, but in the case of fractional Laplacian, I will be more specific about the conditions on these coefficients here, on this vector field, on this real valued function, and also this diffusivity function. The thing what I forgot is in what sense we talk about solutions, and we always mean weak solution, distributional solutions, and this is defined as follows. So such a function, in this case it will be measure valued in general. So there, such a function is a solution. So a measure valued path is a solution to the in the distributional sense to the Fokker-Planck equation. where we just multiply the equation with the test function in space and time, and then we put over all the derivatives into the test function. So it is not to be confused with the weak solutions, where I only take here the divergence over to the test function, because then you have to assume from the very beginning that the rho t is weakly differentiable. Otherwise, you cannot even formulate what is a weak solution. We don't do that. We take a larger class. So for existence, it's easier to find such solutions. And you see it's exactly what I've done here. I take a test function in space and time. I shovel over the time derivative to the function, and I shovel over the Laplacian to the test function. It's written here. And I shovel over the divergence to the test function. And then if you do it in this way, the initial condition will pop up here. Yeah, this is well known how to do this. But I want to really say we want to have a very general notion of solutions, yeah, and it fits exactly the probability. And also for the uniqueness, we have to prove uniqueness in this very large class of solutions. Otherwise, it will not be not helpful at all for the probabilities. For prove, for instance, that this equation is a weak, unique, probabilistically weak solution. And so it's very important to prove uniqueness in this much larger class of solutions. So if we can prove uniqueness, what is called entropy solutions, for instance, is not enough. So we cannot use this to prove any kind of uniqueness for our stochastic equation. Okay, so now finally come to the topic of this seminar series, so the fractional part. We can do the same business. So in the same way, so again, I have a superposition principle, and I have here to go back by Dinkin's formula. If we replace the Laplacian here by fractional Laplacian, this is very well studied, the porous media equation with fractional Laplacian, but now we add also this drift that was not at all studied. And as I said before, for the stochastic part, this will give a drift into a stochastic equation, which is here. So as before on the previous page. And then for instance, we can take this drift in such a way that we get a stationary solution to a stochastic equation, respectively stationary solution to the corresponding Fokker-Planck equation. So that's the main motivation why we do this with the drift, to get maybe a better way to describe certain nonlinear stochastic phenomena, even having a stationary law. Okay, and we need a little bit of, on this S, as you can imagine, we want to perturb it by a first order term, so we need sufficient regularity here. So in order, at least for the uniqueness as well, but for the existence is not really necessary, but for the existence, for the uniqueness result, we need this. And in fact, also for the existence, we need such a thing. So if we want to make this perturbation, we really need this. If this is 0, then we can just take S between 0 and 1. That's not a problem. Okay, and then this superposition principle I mentioned before was known for diffusion equations. So that means if there is a local operator here, but it was not known for jump type operators, so non-local operators. And then in this paper, we proved this superposition principle, which I don't want to explain today in more detail in this paper in PQF. Now look at the corresponding process. The corresponding process has a very similar diffusion coefficient. Yeah. But it is no longer 1 divided by 2, but 1 divided by 2s, because when s is equal to 1, it was the Laplacian. We had on the previous page 1 over 2 here. Now we have 1 over 2s, and we have to replace the Brownian motion by a certain Levy process. And again, please remember this, you have two equations. So you have one equation like this, and there a row appears, and the row must be such that the law of the solution is this row. But if you come from here, we know this row, and this always can give you some feeling how we solve the equation. We know the row, so we fix the row because we know it here and here. And then we can try to solve this equation by usual techniques for stochastic differential equations. Yeah? So then it's just a usual stochastic differential equation. This is just any coefficient that depends on time. Okay, it depends in a complicated way. Let me through the row, but we have the row, so it's just again function of space and time, the drift, and then we can try to solve it using usual techniques. The problem is that usually in these cases, like in the porous media case or the fractional porous media case, this row will not be a continuous function of x. And then you have usually problems to solve an SDE where the solutions are not continuous in the spatial variable. Yeah? But our technique works just under measurability assumptions, so we can solve these equations using this superposition principle, in this case from this paper. Okay, so the corresponding distributional solutions, so they are really weak solutions in the sense that so they're more general than weak solutions in the sense that we again put the whole derivative, now the fractional one, onto the test function. Otherwise, the definition is exactly the same as before. And we call this so weak FP Fokker-Planck equation or distributional Fokker-Planck equation, and this S refers to this S. So small remark before I go into more details how we solve such fractional nonlinear Fokker-Planck equations. I would like to briefly mention one more generalization, and there's a paper on arXiv, which I think I forgot to mention at the beginning. So if we replace now this power S between 1/2 and 1 by psi of minus Laplacian x, where psi is a Bernstein function. Yeah? So we can do exactly the same, play the same game. So we can solve the corresponding stochastic equation, not quite, but we can at least solve the corresponding martingale problem. So the stochastic equation is not, you can write it, but it's not uniquely determined. This is a problem in this for this more general powers of the Laplacian. Okay, but that I don't want to talk about today. I go back to the Laplacian, so the fractional Laplacian. Now, let me explain how we do our first step in the program. The first step in the program is solve this equation, find a weak solution to this equation. We find a little bit better sort of solution, namely so-called mild solution to this equation, but they are weak solutions. And then later on, we prove uniqueness in the class of all distributional solutions. Yeah, so that's important. And then once we have this, by this general technique, we can find the corresponding process and then the corresponding nonlinear Markov process by starting at sufficiently many initial conditions. Okay, so now let's solve this equation. So how do we do this? We do it in an L1 context. This is a nice theory that was developed by many people since many years. So let's say the basic approach is known, and I will talk a little bit about how we implement this fundamental or behind the method which is behind this general method behind it. Okay, so now we go back to the PDE notation. So the rho is again U. So forgive me for that, but it's easier than to compare with the results in the paper because we call it also the U. And so what do? We want to solve this. It's a Cauchy problem, right? We want to take the derivative. So this stands now for derivative. This should be the same as this on the right-hand side. So we put that to the left-hand side. And we have an initial condition. So U0. So we first do this, or we want to do this first for initial conditions in L1. So this should be an L1 function. So then we have a Cauchy problem in L1, right? So here's the derivative. Here an nonlinear operator acts on U. So we want to solve this as a Cauchy problem on L1 of over RD with Lebesgue measure. Yeah? And we need that D is bigger than 2 because we have to work in homogeneous Sobolev spaces in the case, so it's just at the moment D is still bigger than 2, but at some stage later on we need strictly bigger than 2. Okay, and then minus, this is the operator, so how do we define this? And we do it, of course, by Fourier transform, but not just in L2, because, as I said, we would like to solve this equation on L1, yeah, this Cauchy problem. Okay, so we take a larger domain for minus Laplace to the power S, and we do the following. So we take the Schwartz distribution space, so we find the domain of this operator minus Laplace to the power S. We take all U and S prime so that it's Fourier transform. So this initially is an object in S prime, and we demand that it isn't locally L1 such that psi to S, so this is the variable. So this I consider this as a variable of psi. So I take this variable of psi, this function as a function of psi. So I take this function of psi and multiply by, so I apply to psi and I multiply by psi to the power 2s, and psi is a point in RD. No? Okay, then I get a new object, and we assume which is a locally integrable function, because I assume that this is a locally integrable function. So I can multiply by this function, which is also locally integrable, yeah, and it's locally bounded. So that means this is a locally integrable function. So I can think of it as an object in S prime. Yeah, so I do not know what this is. Yeah, but I just assume it's locally integrable, and then I would also like this is in S prime. Okay, so now then this is my domain of my operator, and then I can define this operator by Fourier transform. So it acts on U in ds by just so I want to define this object and then define equivalently its Fourier transform, and it's this. So that's exactly what you would do, yeah, and to define this operator. And I want to define it on a space which contains L1. Yeah, this definitely contains N1 because it's an S prime. Okay, then you take Fourier transform in S prime of L1 so something that we assume it's in L log 1, so it must be in L log 1. But if you take Fourier transform of something in L1, you have this, and then the next one is you have to check this, but this is all verifiable. Yeah, so it's really in this space. Okay, so then we have this definition. So where S stands for the Fourier transform in RD. So this I use this kind of definition. So with two. So this is a definition people prefer in analysis. Probabilists don't put this factor, but it's better to put the factor here to get the constants right. And we call this non-linear, non-local Fokker-Planck equation. We want to solve it now on L1. And you do maybe hypothesis. So the hypothesis now on the beta. So it's a C1 Lipschitz B of 0, 0, and we need that this beta is increasing because we want to use the theory of accretive or monotone operators. So we need that beta prime is positive. So beta is increasing. Okay, and we need really strictly increasing in our proof. And then the D is this was the drift in the transport part, so the vector field D that appeared there. So it should be C1, and I forgot here should be also bounded. So this is just missing. Divergence in L2 log, so these are local conditions. Then B is supposed to be just bounded, let's say, and continuous. And this is on div D is a global condition, so its negative part should be in L infinity, and B should be greater or equal to 0. So these are the minimum assumptions we need. It is a large class of betas, Ds, and B that we can handle. And then we look at the operator here on the right-hand side, and we want to define it as an operator on L1. And here it is defined. So it's we take the domain of this operator, we call it A0, all U in L1, such that if I apply the operator to it in the sense of distributions, it's again in L1. So I take sort of the maximal possible domain of this operator here, which is defined always in the sense of distributions. But I take the maximal one, so in the sense it should be on L1, so all U in L1 for which this makes sense as an object in L1. It follows, by the way, automatically if you take such a maximal one that this operator is closed on L1. Okay, now we want to construct a solution of the Cauchy problem. So what do we want to construct? Well, if you think of this, this is an operator, so we have a Cauchy problem to solve. So some of the solutions would be e to the power exponential of this operator times t. That should be the solution, just formal computations with symbols. Yeah? Okay, but how do you construct a semigroup, whether it's linear or not? By Euler's formula using the resolvent. And that's exactly the technique we use. Famous theorem behind that in L1 is the Crandall-Liggett theorem. But first of all, we have to construct the resolvent. And in here, I explain how we construct the resolvent a little bit. It's a nonlinear resolvent. The resolvent is a solution. So we take an f and we find a function, we call it j lambda f. So it solves this equation, 1 plus lambda a0. So that's now an elliptic equation. Yeah, so it's just here's the identity operator, and this is now just an operator in space, because these are all spatial derivatives. Okay, so we solve this, and the corresponding solution somehow is the inverse of this operator. It is so far only the right inverse. So if we can solve this PDE, it's a PDE, F given in L1, so we can solve this, then we are very close to have found a family, because here's a lambda, family of operators, and it turns out we can construct this in such a way, it's no longer linear, but there are Lipschitz constructions. So there are Lipschitz on L1, this map from F to J lambda F, which is again a function in L1 in the domain of A0. So means A0 of this is again in L1. So everything is well defined. There's no dodgy business. It's absolutely rigorous. And the J lambda is a Lipschitz map with Lipschitz constant less than 1. So that's how you can construct it. And it satisfies the nonlinear resolvent equation. So that describes the relation between the J lambda for different lambdas. Okay. And from this resolvent equation, it follows immediately that if you look at the image, the whole image set, the range, so you take J lambda of L1, all the functions you get, yeah, because from this map that we construct here. If you take this image set, this will not depend on lambda. So that is typical for a resolvent. So J lambda of L1, the set, the image set, is the same as J lambda 2 of L1 is the same as J lambda 1 of L1. This follows immediately, and this is the significance of this nonlinear resolvent equation. And besides the J lambda, because this, remember, this was an operator with divergences everywhere. So here's this is a sort of fractional divergence, and here really you have the divergence. So it should conserve the mass and in time, and it does. So we have this property. So the L1 norm is not changed. If the right-hand side, if the right-hand side here is an L1, this is, and look at the L1 norm of the right, not the L1 norm, but this without absolute value. You look at this quantity, let's say, the mean, then this is the same as the mean of the solution. Okay, then also it is positivity preserving. So if F is positive, then J lambda F is positive. And the next one is that this J lambda is not so you don't have the maximal principle in the sense that the solution, the norm of the solution, the subnorm of the solution less than the subnorm of the right-hand side, but you have it less than the subnorm of the right-hand side up to a constant. That depends on this D. So if the D is 0, so there is no drift, then you have the full maximal principle. And also it has kind of a smoothness property. So at least if you apply beta to it, then you end up in H1, the Sobolev space of the homogeneous Sobolev space of order S. And that's this is sort of important because then the beta U, you can also then apply this. And you know this is this element in the Sobolev space of order S. So if you apply this, you go into the Sobolev space of minus S. Okay, so this is a regularity that you get for free by this contraction. Okay, so how do we do this? Well, basically we approximate the operator A0 by operators with beta coefficients. So by such a guy, and we also make this power of the Laplacian a little better by adding this epsilon. And then we first of all solve this equation, and then we let epsilon go to 0 to get rid of this, and then we have beta here, then we have exactly the solution. So identity plus, so we want to solve this, identity plus this A0. Yeah, we want to find a solution. So we do it first for this beta equation. We replace this A0 by this operator, this one, and we smooth beta and B and delta. And I've written down how here, but there's not time to do this in detail. Anyway, when epsilon goes to 0, then we prove that the corresponding solutions converge to the solution of this equation. Beta epsilon converge to B, beta, the B epsilon to B, the D epsilon to D. And then we prove that the solution converges. That is the most of the work. Okay, and then this J lambda is right inverse of the 1 plus lambda A0, and then we just restrict this operator on the image of this operator, and then we get that this operator is a bijection on this smaller domain. And this is our operator A. And this we can now invert, as I just explained, and then this gives us a nonlinear resolvent. Okay? And the corresponding operator has all the properties we need to apply Euler's formula. So defined above is M accretive. So these are technical terms. I don't, probably most of you know them anyway, but I don't want to recall them. So they are has certain properties, so that we can use Euler's formula and also the domain of this operator, which I defined before. So it is simply this one, the J lambda of lambda 1, which is a subset of the original domain. It is still dense in L1 if beta is smooth. Yeah? But this is only true if beta is smooth. And then we can use Euler's formula. So that is a theorem granular ligate. So we just take this resolvent 1 plus lambda a to the minus 1. This is my lambda, and now I iterate this operator n times. I take n to infinity, and I get an object, which I call ST, depending on this t, applied to the initial condition, yeah, which only works for initial conditions in the L1 closure of the A. But as I just said, this is equal to L1 if beta is smooth. Then we can do it for all u in L1. And then we look at this formula, and we can prove that this converges in L1, even locally uniformly in T. So that gives me an operator, which I call S of T, which is basically the exponential applied to U0. This follows from this general theory. And then one proves that this ST from L1 to L1 is a semigroup of contractions, and it solves my equation. So I just solved the Fokker-Planck equation for all such U zeros as initial condition. And so therefore, this is a solution to the Fokker-Planck equation, this function. You see, this is a function. ST is an operator in L1, this is in L1, this is a function in L1. So it gives me a function in T and X, and this solves my, gives a distributional solution to my Fokker-Planck equation with a fractional Laplacian. And then you see, if U0 is bigger than 0, we learned that this with the -1 here is still bigger than 0. It's positivity preserving. So the iterates are also positivity preserving, hence is the limit. So we also have the positivity preserving property. If U0 is positive, STU0 is positive. And for the same reason, it preserves this property that the mean of the initial condition is preserved. Yeah, U0. And okay, so this is the same as this. So ST of U0 is the same integral as U0. And finally, if the initial condition is in L1 and L infinity, one can prove that the solutions are bounded in space and time. So STU0 as a function of T and X is bounded. And in that case, when we take a bounded initial condition, we can drop the Lipschitz assumptions on beta. Yeah, it's enough just that beta is C1. So we have just solved our Fokker-Planck equation. Now, we also have a uniqueness result, but the time is now running up, so I will not give you this uniqueness result, but just now if we look at this type of condition, so this is a pure uniqueness result. So we assume we have two solutions, yeah, two distributional solutions, and then we want to, with the same initial condition, and we would like to prove they're the same. So that we do not have to repeat the hypothesis for existence, yeah, because we just assume they exist. So for existence, these were the hypotheses, yeah, plus this, what I forgot, they should be bounded. But for the uniqueness, we just take two solutions, so no worry about existence. And then we need either similar condition as before, beta prime positive, and so on. But here we need much less. And then we can prove we have a unique distributional solution. The proof is not so easy, but anyway, so that is our uniqueness result. Okay, and then, yeah, because time goes a little bit fast, so now let us apply it to the McKean-Vlasov SDEs. So we go back to our picture, the very beginning. So this is now best to explain it there. So we have found a solution for this equation. So then we use this result from here, what is called now superposition principle, and then we get a solution to this equation. So I do not want to formulate it. The only thing I would like to tell you is what kind of Levy process you get, because this might be of interest to some of you. And here is the Levy process. So I don't give you more details, but just this. Okay, so the Levy process is a d-dimensional, as you can imagine, isotropic 2s stable process L with this Levy measure. So a little bit more precise, so I can, and then we have this equation as from the previous slide, and then here a little bit more precise. So we can construct a Poisson random measure n with intensity, this measure, and then we take this Poisson measure minus its compensator. We get a martingale. So then this is the martingale part of my Levy process. So for the small jumps, and this is the large jumps bigger than 1. And this is my process. So that's a Levy process, and this is the one that you have to put into the noise. In order, now you can ask how do you find it, and this is simply by trying to find a good formula for this operator. You know? Because if you look at the equation that we want to solve, then this should be the square of this should be the diffusion of our Levy operator. And here, that's exactly what we do. We take this square, and then we try to put it in front of the Laplacian, because that is what one should do. Yeah. So then we put it in front of the Laplacian, and then we rewrite it in a certain way, which we can do in this situation, and then we really find exactly this Levy process that will be the noise. So this is for expert. This is, I mean, more or less standard to do that. You know? But it's just that to rewrite this operator with respect to this Levy measure in a certain way, and it works in this case. It doesn't work in the general case for general Bernstein functions, as I already said. Okay, so once we have this process, then we can also prove uniqueness of this process. So I just tell you, so then from the results we have, we can also prove the corresponding solution of the McKean-Vlasov process is weakly unique. So two weak solutions have the same laws under the assumption that the time marginal laws are bounded. Without this, we cannot proceed. But that is enough to prove Markov properties. And then the last part is now about the Markov processes. So how do you get a Markov process from an SDE? Well, you look at all possible initial conditions for which you can solve the SDE, and you look at the corresponding path laws, that you get from these solutions. So you get a family of measures on path space, and you check whether they're related through the Markov property. The difficulty is here that the Markov processes depend on time. So we have to do it we have to start the SDE for every time and every initial conditions in order to get the corresponding time inhomogeneous Markov process. So then by our results, we can prove that this family, so if you take, for instance, these initial conditions, so all probability measures with the density, and of course in L1 and in L infinity, and then we solve our corresponding McKean-Vlasov equation, and we start it from S with this law. This gives us a solution, and by our results, and then we look at the corresponding laws. And now this family of laws, they then are a Markov process in the sense of nonlinear Markov process in the sense of McKean, and the most important property is here the Markov property. That's what they fulfill. So you see this is sort of the sigma algebra of the present. R is the present. Here we start present time, and you try to calculate an event from the future. This is just a valuation map on the path, given the present, given in the past up to the present, and this only depends on the present, where you are presently with your process. And this is a regular conditional probability of this conditional measure. Yeah, you stop at the present, and then you predict what happens in the future, given where you are at the present. So then you get exactly this kind of process. And the non-linearity, you might ask, for me, this looks exactly the same as in the linear case. The non-linearity lies, if you look at the laws, this will no longer be a convex function in Z, because this is a solution, in Z. Will no longer be a convex function, no longer be convex in Z, and you do not have the Chapman-Kolmogorov equation, but you have instead this flow property between the path laws. And this makes a very, very interesting probabilistic object, this kind of observations about this nonlinear Markov process. Okay, but now I want to stop. Thank you very much for your attention.
Thanks, Professor Röckner, for the nice lecture. For questions, please raise your hands. I'll call out your name in the order they appear on my screen. I already see that Professor Scalas has a question. Please go ahead.
Yes, so can you hear me?
Yes, very well.
Very well. Thank you very much for your very interesting talk. So I eventually understood, I would say intuitively, the reason why one uses nonlinear Fokker-Planck equations, thanks to the first 2 or 3 slides. And I would like to ask you, in fact, a couple of questions on those initial slides. One is some triviality, let's say. So in the nonlinear Fokker-Planck equation without drift that you write down, you have an absolute value of u. It's this one, yes. But u is the same as the solution. So you are looking as a positive function that has the meaning of a probability. So is this absolute value really needed? And the second question is, considering the process that you are defining and studying the nonlinear Brownian motion. So for Brownian motion, there is a definition, or better, an existence theorem based on Donsker's theorem and invariance principles. Is there anything like that in the literature for nonlinear Brownian motions?
Okay, so I can maybe start with the second question.
Yeah, please.
So this is still to be examined. So there is no such result in the literature so far. What you can do is you could try to solve the stochastic differential equation directly by trying to use propagation of chaos. But as far as I know, this has not been done. There is a very nice paper by Jean-François Jabir and Miri Bossi, sorry, and they also find a solution to this equation. And they use more probabilistic methods, yeah. But nevertheless, so far I do not know about any invariance principle-like characterization of this process. It would be great, of course, to have it, but it would also be great to understand what is different from Brownian motion, you know, because now it's a new probabilistic object, and of course we would like to see sort of the difficulties from the porous-media equation or the special properties of the porous-media equation. We would also see it in the for the process. In particular, when m is less than 1, the solution has the property to get extinct in finite time. Yeah, so and this is a property that we have so far not a very good probabilistic counterpart, and to see what happens to the process also would be really very nice to understand. Your first question, one can I don't know, I did something, just a moment.
You are magnifying essentially, yes, but
okay, no, it's fine. You're right. So then what is important that you have an increasing function of u. So the beta of u on the next page, yeah, was an increasing function of u. Remember, we assume beta prime positive. So therefore, we just write the power here in the way that it's a positive function of u. But you're completely right. One can prove, as I said, if the initial condition is positive, so in this case a positive measure, then the solution is positive, and then you can drop it again.
Ah, okay, great.
Okay.
So there is a theorem somehow that
exactly. But
so
of course,
you have the Laplacian applied to u to the n somehow.
Exactly. And of course, you have to start with this equation to prove that, but once you know it, then you can drop it again.
Of course. Thank you very much.
Do we have any more questions? I don't see any raised hands, but if you have any final remarks or something, you can unmute your mic.
Okay, I have another question.
Yes, please go ahead.
Sorry for all of you, but this was very intriguing for me. So yes, when you go to the non-local equation, you use the fractional Laplacian, and you have corresponding equation where you use Levy noise instead of white noise.
Right.
Standard. Yes. Now Levy white noise instead of standard. Now, if of course you are considering stable laws and stable white noise, but now suppose you use another Levy process without the transformation with the Bernstein function, just the semi-group generator of the Levy noise. Have you already started studying this problem?
You see, there is a literature about the case where you have the porous-media equation like this, and you take a general operator And if you like Dirichlet forms, then it's a general operator of a Dirichlet form, which is transient. That's important, transient Dirichlet form. And then you can solve this equation. Yeah, there is a solution theory for that. However, it is mainly developed in the not in L1, but in H-1.
Okay.
Okay. So then but also in this theory of monotone operators, there is a famous result, I think one that is due to Bresis, where you can put here any accretive operator. Yeah, maybe you need cyclically monotone. This I don't remember. So there is a general theory to solve equation of this type with more general operators here, and they don't have to be local. Okay. But then the question would be, can we apply the superposition principle in this paper that I mentioned? And this is not so clear for all such non-local operators, but for a certain class we can, because here this is quite a general result. We need that this is is an operator which you can, when you write down, you use it by just writing it out in terms of principal values of integrals, where you take the difference of the functions where you apply it to, so you can characterize the corresponding kernels in such a way that we have this corresponding equation. However, we cannot write the equation in these cases. Like for the Bernstein case, we cannot write, let's say, at least not a unique equation, but we can solve this equation in the sense of a martingale problem. Yeah. So like for the Bernstein case, that's possible. But we have not done that, and I'm not saying that everything is easy. So I think it is worthwhile to look into this. Yeah, because otherwise there's no research anymore. You say, okay, it can be done more generally. I hate that. Yeah, I really want to say we have done this, and I think we can do also more general research.
Exactly.
It is hard work.
Related to possible. I mean, if people had already done, but for people who are in the audience, maybe even for myself, is some stimulus or stimuli to have maybe some new papers or whatever.
Right. And I don't want to stop. I don't want to stop you. I want to motivate you.
Thank you very much.
All right, do we have any more questions? I don't see any raised hands, and so I assume there are no questions. So this is a good point to stop here. Thank you very much, Professor Röckner, for the nice lecture. It was very much interesting.
Okay, thank you very much. Thank you very much for your attention, and have a nice weekend. Bye-bye.
Bye-bye.